Hi, good afternoon. Okay, so during the last 2 days we heard a lot about datasets. This one? Ah. No? Okay. So during the last 2 days we heard a lot about datasets, a lot about accuracy, how to calculate that, how to evaluate if something that you have done on NILM is good enough or not that good. And in order to do that, but also in order to improve ourselves and the services we provide for our clients, we wanted first to make a very big as possible data set with ground truth data, but also with mains data. And then based on that, trying to improve the algorithms we use and continuously evaluate the accuracy we're able to achieve before delivering something to a client. And that's actually what we will talk about through this presentation. I'm representing Net2Grid, but I think that you already know that. So how to create a data set. Before starting collecting data and building such a data for ourselves, we spent some time thinking about that, and we understood that, of course, we would require equipment. We were lucky enough because that equipment was mostly ours, so we produced that equipment ourselves, so we could get access to data more easily than others. But of course it costs, it takes a lot of time, and requires a lot of people that are helpful enough to continuously help us to monitor that everything is connected and be sure that the data is delivered on our side. Of course, another thing that we need to take into account is that we need long-lasting experiments and long-lasting data gathering, because otherwise we might miss really important information about the seasonal behavior of appliances. We also came up with a really difficult task that we need to fully understand how the same appliances operate under different programs, and how the same appliance type, like for example the washing machine, can behave if there's a different mechanism inside that. And we wanted to have all this information in place in order to have such a good data set. And of course, in order to do that, we have collected ground truth from smart plugs, but together and in parallel with that, we have also collected the mains data in order afterwards to test our algorithms on that. Just to give you an understanding how big the dataset is, we have over 200 different kinds of washing machines, over 350 kinds of dishwashers, more than 250 kinds of different ovens, and 150 plus of different dryers. And in terms of events, in terms of final end users of those appliances, usually we're talking about more than 5,000 or up to 20,000 different events, in order exactly to capture this great variety in terms of patterns and behaviors. Since it's already a year now that we are offering NILM services also for houses that have solar installation, it was really important for us to collect ground truth in terms of generation, electricity generation from houses with solar. And we have such information from 500 houses over a period of more than 1 year. So after that, we had a lot of data to go through and try to examine and analyze them in a lot of different ways, trying to get as much juice out of that. And what did we do? Of course, we have isolated a lot of different energy-related metrics, but also other ones that are like statistical ones that you can find in a lot of different applications. And for the whole dataset, for all events, but maybe also for specific parts of those events, we did an extensive analysis for each appliance type, trying to extract features that would help us to model good algorithms. So that's an example here. For example, here you can see that we have about 200 houses, all the events for a specific appliance, and we are examining what is the energy consumption per event per house. So what you can see on the right side is actually thousands of different washing machine events, and maybe washing machine, I'm not sure, maybe it's dishwasher. And on the left side, we can see that average. That gives us a very good understanding as a first page of a big report about what is the energy consumption per event for that specific appliance we should expect. Another thing we did is that we did something like a distribution fitting of all the events and everything we had gathered in our data set. And we tried to find what is the distribution that maximizes the likelihood function of the data that we gathered. And for us that was important also because we wanted to correlate the energy estimation for a specific event, for a specific appliance type, just by being able to detect something on that end use, on that event that was maybe easier to be detected. For example, since most of you are familiar with such events, usually you work with specific big pulses in the range of 2 kilowatts or even more, and the remaining energy consumption per event that is here and there is hidden and can become a mystery. So through this data set, we have correlated the energy consumption of specific parts of the event with the total one, increasing our accuracy in terms of the energy estimation per event, not in terms of the detection, but in terms of how good we calculate the energy estimation per event for each appliance of interest. And of course, since the dataset is quite big right now and becomes bigger since we still have a lot of smart plugs installed, we could also do something like a time of use analysis. And we can also derive useful information about how often an appliance is being used, which days are the ones during which a specific appliance is used and how many times. If we can see that there is a seasonal difference for appliances. For example, in Greece, we don't have so many dryers because the weather is usually good and we just hang our clothes outside in the balcony. In Northern European countries, we don't have that, and especially during winter, our dryers are used more often. This kind of information and this kind of knowledge, since it came up after going through a lot of thousands of different end users, becomes important and can be, of course, used as an additional layer of information when you want to provide a bit more accurate AMR-related NILM. So, since if you want to work with AMR data with 15 minutes or 30 minutes resolution data, you need a lot of additional information to make that good. That information coming from ground truth is something that can be really useful. In addition to what in the previous slide was mentioned, we were also doing analysis about which day is the one that some types of appliances are more frequently used, and if some of them are being used more often and more times per day, or maybe 2 times or even more, in which day that happens and which appliance is the most possible to be seen there. And then we stopped and we said, okay, let's see, what else we can do with all this data? Is that all? Is that all like statistical analysis and time of usage analysis, maybe better because we have more data, but that's all? So we tried to find out if we can make something better, something more. And since we have the energy consumption per event for some thousands of events, and we have also the appliances, if it's a washing machine or a dishwasher, we tried to correlate that and we tried to transform this information in something that has to do with the heat, the temperature maybe that washing machine has been used, and if that's good enough or bad enough in terms of energy efficiency. So based on all this data and based on this dataset, we are now able to distinguish if a washing machine, also the duration is important here, I forgot to mention that. So now we're able to detect and distinguish events that are washing machine events, for example, that are either at high temperature or low temperature, that are low energy or high energy. That gives us a lot of information that can be passed to an end user for him to understand that maybe he shouldn't use his washing machine at 90 degrees because that consumes a lot, and maybe that's something that he can change and do that in a better way in the future. So this slide here actually sees how we are being transferred from the energy and the duration of the event in information like the temperature of that. And I know that during the last 2 days, there's always the discussion, also during the previous conferences, how do you calculate accuracy, how accurate you are. Some say that are like 90%, some others are not mentioning about accuracy, different practices. What are the KPIs that should be used in order to calculate that? For us, when we do an analysis for a client, for a pilot tester, for a proof of concept, usually the three metrics that are of critical importance are the event detection, energy estimation, and false positives. By event detection, we mean how many events of a specific appliances were detected. So if you have 10 washing machine events and you detected 9, of course you have 90%. By energy estimation, for the events detected, we mean that how accurate the energy was calculated for an event compared to the information coming from ground truth. So if we have for a dishwasher 1 kilowatt hour and we did that, we calculated that with a deviation of plus minus 10%, 15%, then we think that we are within this limit and then that we are good. And false positives, of course, are always there because the more false positives are, then the customer becomes dissatisfied and doesn't want to use an app for something like that. So the results that you will see here are based on these three KPIs with the weights that I have assigned to them for your understanding. And by means of before, you will see results we were able to achieve for the 4 most important energy-intensive appliances in a house. And by means of after we have collected the data set and improved and our algorithms and our whole approach. You can see that the improvement is high, especially for the resistive appliances. And we didn't have a lot of ground truth information before that. You probably know that it's quite difficult to get ground truth information, especially for appliances like ovens. So before that, it was a mystery, and it was also this difficult thing to identify if something is a dryer or an oven, or how to distinguish different resistive appliances with each other. But the improvement was evident not only for the resistive appliances, also for the dishwashers and the washing machines. And in order to examine the improvement before and after, we did a test with 100 installations, for which, of course, we had also the ground truth in order to be able actually to compare with something. And these are the results. And on the corner right down, you can see 4 graphs. And the reason we have this is actually an expansion of the graphs above for the washing machine and the dishwasher. And what you see here is before and before 3-phase and after 3-phase. As Bert mentioned yesterday, together with Peter, for our project in Germany, the Iona project, we have access to 1-second resolution data coming from all 3 phases. That gives us the opportunity to work instead of the total with the 3 phases individually. And by doing that, we're able to work with less noise, and we are able to be more sure that an appliance is connected to a specific phase, which also becomes a part of the model that is being saved for that appliance afterwards. So as you can see, even before the dataset was built, but also after, when we have access to 3-phase data individually, the results become better and better. That's something that also Bert presented yesterday, and it's clear that the significant improvement we were able to achieve in our results has been made after the dataset was established, was in our hands. And something that Bert didn't spend a lot of time yesterday to discuss is that, okay, the accuracy has been improved, but what has been improved significantly over the last 6 months is the coverage. And I want to say something about that. Maybe some months back, we were thinking that an oven or a dryer is something really specific, but after collecting more and more data, we came up with a lot of different patterns, a lot of different figures, different kinds of appliances of the same type that we never had an understanding how they work, and that they actually represent an oven or a dryer or a washing machine. So this data set did not always help us improve our previous algorithms, but also helped us to add additional modeling approaches for other types of the specific appliance. So the portfolio we're now able to support is far bigger. And that's why I have here two slides, this one and the next one, about did we solve everything? For example, here you can see 3 figures on top of the page from washing machines and 3 figures in the last part of the slide about dishwashers. Maybe 1 year back from now, we would say that for us a washing machine was something like the middle, but it's not always that. You can see that in the same house, the same washing machine can operate with a lot of different pulses or even without the pulse. And that is really important. I mean, our previous approach would have detected one of those, but now we're able to detect different programs for the same appliance, for the same house, regardless of the way someone operates his appliance. The same for the dishwasher. That's for the same house. We can see a 2-pulse behavior, a 3-pulse behavior, but also a 4-pulse one. And even if we were able to detect the last one as a 2-pulse dishwasher, and that means that we would have missed 2 of the pulses, so the energy estimation KPI that I previously mentioned would have failed. So it's extremely important not only to be able to save a model for a specific appliance in a house, but also to be able to see if that appliance is being used in a different way and how that is translated in terms of power consumption. And that's also the reason for sometimes we are doing this recursive training process Bert presented yesterday, because if someone uses his washing machine during the training period with only a way, then we will probably need more time in order to save more models for that appliance. So here we have this presentation of washing machines and dishwashers, and here we have something that is more interesting, and it's about ovens and dryers. You can see how different and how difficult that can be. And for example, in the first 3 screens, you can see 3 different types of dryers, and in the latter 3, you can see 3 different kinds of ovens. For us, the middle one in the last 3 graphs looks like an oven. You can see ovens that work in a totally different way, and that's what we're trying tonight to do. We are trying to add more and more appliance types in our portfolio in order to be able to work with more and more houses and more countries around the world. So I have some conclusion bullets, which probably I have already discussed about. It's to provide NILM, accurate NILM, regardless of the way that someone calculates accuracy, requires a continuous effort and a lot of high quality data. It's something that needs a lot of attention over a long period of time. And when you have a large data set with ground truth information, that can help you first to understand better how specific appliances operate, then be able to distinguish which is what, and then translate also different operation modes to specific load signatures, which of course all this information can be then translated in better business cases by your colleagues. I would like to thank you for your attention. Here is a slide. If you're interested about our NILM service, most of my colleagues are here, so you can discuss with. If you're an academic, someone who would like our help to collect data to do his work, we're always willing to help you. You can just drop me an email. Thank you very much.